Power Series Part 2. Examples. Example. The sum of n factorial x minus 5 to the power of n. We will apply the ratio test because we have factorial. Here is the setup. From x minus 5 to the n plus 1 over x minus 5 to the n, we will get x minus 5. From n plus 1 factorial over n factorial, we will get n plus 1. Now we have to take the limit of n approaches infinity. We have two possibilities here. When x is not 5, this is the limit of a constant times n plus 1, which is infinity. When x equals 5, this is the limit of n approaches infinity of 0 times n plus 1, which is just limit of n approaches infinity of 0, which is 0. Now we would like this to be less than 1. This is not going to be less than 1 when x is not 5. But when x is 5, this is always true, because we get 0. 0 is always less than 1. So this is going to be true only when x equals 5. So we can conclude that the series absolutely converges only for x equals 5. And that's why the interval of convergence is just 5. And the radius is 0. Example. The sum of x minus 1 to the n over n factorial. Because of the n factorial, it will be really easy to apply the ratio test. Don't forget the absolute value. We are going to rearrange nicely all the terms in the limit to get that. X minus 1 to the power of n plus 1 over x minus 1 to the n is just x minus 1. And n factorial over n plus 1 factorial is just 1 over n plus 1. Now we have to take the limit when n approaches infinity. Now for all values of x, we're going to get 0. And I would like this to be less than 1. I want to note that what's going on here, that x minus 1 is fixed. Even if x is a huge number, x minus 1 in absolute value is a fixed number, while n is getting greater and greater and greater and larger and larger and larger because the limit of n is infinity. We can observe that this is always true, because always 0 is less than 1. We didn't use any information about the x's. It means that we can take any x that we like. So r is now going to be infinity. And the interval of convergence is just the set of all real numbers, which is the interval negative infinity to infinity. In this case, the series absolutely converges for all x's. Example. The sum of x minus 4 to the n over n ln of n to the power of 2. We will apply the ratio test. In order to simplify the computation of the limit, as you can see here, instead of taking something that has 2 terms to the power of 2, I have the first term to the power of 2 and then the second one to the power of 2. So I get n plus 1 to the power of 2 times ln of n plus 1 to the power of 2, and then I get n to the power of 2 times ln of n to the power of 2. Now we are going to rearrange the terms, so like terms are going to be written together. You may start taking the limit now, but I think that it will be much nicer still to simplify a little more. So obviously x minus 4 to the power of n plus 1 over x minus 4 to the n is just x minus 4. And then I included in the power of 2 n over n plus 1 instead of n to the power of 2 over n plus 1 to the power of 2. And I did the same with the ln of n and ln of n plus 1. Now, one step of L'Hopital will give you the limit of n over n plus 1 to be 1. So to the power of 2 is 1 to the power of 2, which is 1. Another L'Hopital applied on ln of n over ln of n plus 1 will give you that the limit of this is 1 to the power of 2 is 1 to the power of 2, which is 1. And we get absolute value of x minus 4. This is like the L in the ratio test, and we want this to be less than 1. The first observation is that the radius of convergence is 1. The second is that the interval is centered at x equals 4. So here is x equals 4. Here is the circle of radius 1. We get 2 endpoints. One of the endpoints is 4 minus 1, and the other is 4 plus 1. We know now that the series absolutely converges between 3 and 5 and diverges outside. But obviously we have no idea about the convergence of this series about x equals 3 and about x equals 5. For this we will need to check the two endpoints. We will start by checking the endpoints at x equals 5. When we substitute 5 for the x, we are creating a new series which is not a power series. It does not contain x. The term now is only an expression of n. We will use comparison test with the series of 1 over n to the power of 2, which is a convergent p-series with p equals 2. Recall, if we have a p-series with p that is more than 1, then the series is convergent. This is clearly true because n ln of n to the power of 2 is greater than n to the power of 2, and it is in the denominator. So we get that this is also converges. If we take the absolute value of this, we will get the same thing, okay? So we can say absolutely converges or converges. Now we will check the other endpoint at x equals 3. We substitute 3 for x, and we get that. We observe that this is the alternating series of the one above. So if we will take this in absolute value, we will take exactly the same series as we got at the endpoints x equals 5. Because this series converges, and even absolutely converges, it's clearly that this one is also absolutely converges. We can conclude then about the other endpoint. And now we can summarize and get the answer. We know that the radius of convergence is 1. And what about the interval? We should include the endpoints. So the interval is between 3 and 5, including 3 and 5. We also know that the series absolutely converges on 3 to 5, which means all the x's between 3 and 5, including 3 and 5. Another example. The sum n runs for 1 to infinity of x plus 3 to the n over 2 to the n. In this case, we can apply the root test. In this example, the term is a function without n to the power of n. This is the easiest clear case in which you prefer the root test on the ratio test. But don't forget the absolute value. We get here that the limit when n approaches infinity of the nth root of the absolute value of x plus 3 to the n over 2 to the n is absolute value of x plus 3 over 2. Now we need to solve that to be less than 1. We get that x plus 3 in absolute value has to be less than 2. It means that the radius of convergence is 2. Minus 3 is the center of the expansion here. Let's draw that. Okay, we start with minus 3 and we take radius 2 both sides. So we get negative 5 here and we get negative 1 here. This is just negative 3 minus 2 and negative 3 plus 2. So we have two endpoints. Between the two endpoints, the series absolutely converges. Outside, it is divergent. And we still need to check the two endpoints. We start by checking at x equals negative 5. We substitute negative 5 and we get the sum of negative 1 to the n. Definitely diverges. Okay, this is simple because even the limit of the term when n approaches infinity is 1 and it's not 0. So we know what happens at negative 5. Now we will repeat the process at x equals negative 1. And we will get sums of 1. Clearly, again, as above. Okay. Diverges. So it also diverges at other endpoints. So actually at two endpoints, this series is divergent. And the answer is R is 2. And the interval is between negative 5 and negative 1 without the endpoints. The end.